We're going to work on an ALEKS problem that deals with determining the rate law equation from initial reaction rate data. In this particular example, they've given us a table with the concentration of the reactants and the initial rate of reaction for 3 different trials. They are asking us to determine the rate law equation, and they also want us to determine the rate law constant to 2 significant digits with the correct units. So this requires some work here. I want to remind myself that the rate law equation is rate equals K times the concentration of the first reactant raised to the power of m times the concentration of the second reactant raised to the power of n. What they want us to do is basically determine the power m and to determine the power n and the rate law constant. So we take a look at our table and we want to try to make the math as easy as we can. For us to solve for m, we want to try to cancel out the concentrations of I2. Take a look at our table. In trial 1, our concentration for I2 is 0.732, and our concentration in trial 3 for I2 is 0.732. So for us to solve for m, I want to cancel out the n, the I2 concentration. So I'm going to divide these two rates, the rates of these 2 trials by each other. But again, I want to make the math as easy as I can. So I want to make sure that I put the one that has the larger rate on top as the numerator and the one that has the lower rate on the bottom. So in order for me to solve for m, I'm going to divide the rate of trial 3 by the rate of trial 1. Let's take a look at solving for n. For me to solve for n, I want to try to cancel out the concentrations of H2. Take a look at my table. I see that in trial 1, the concentration of H2 is 1.77, and in trial 2, the concentration of H2 is 1.77. So I want to divide the rates of trials 1 and trial 2, but I want to put on the numerator the one that has the larger rate. So I'm going to be dividing trial 2 by trial 1. Once we figured out the m and the n, we can go ahead and solve for k. So let's get started on this one. So we want to solve for m, and I'm going to divide the rate of trial 3 over the rate of trial 1. So this is rate equals K times the concentration of H2 raised to the power of m times the concentration of I2 raised to the power of n. Divide that by trial 1. Rate equals K times the concentration of H2 to the power of m times the concentration of I2 to the power of n. Okay. My I2s cancel out, my K's cancel out. So now what I'm going to do is divide 3.07 divided by 0.952. This gives me 3.22. 5.71 divided by 1.77 is 3.23 and raised to the power of m. For me to get that power m down on the floor so I can solve for it, I'm going to take the natural log of both sides. So the natural log of 3.22 equals that m comes down, and I'm taking the natural log of 3.23. The natural log of 3.22 is 1.169. The natural log of 3.23 is 1.172. divide 1.169 divided by 1.172, and m equals 1. Let's go ahead and solve now for n. For n, I'm going to go ahead and divide trial 2 by trial 1. So rate equals K times the concentration of H times the concentration of I2 over trial 1 equals rate times K times the concentration of H2 times the concentration of I2 raised to the power of n. Okay, I see that my H2 cancels out and my K's cancel out. So now I take 4.23 divided by 0.952 and I get 4.443. 3.25 divided by 0.732 is 4.40 to the power of n. I want to get that power n down on the floor so I can solve for it. I have to take the natural log of both sides. That gets my n out of the power. The natural log of 4.443 is 1.491. And the natural log of 4.40 is 1.491. Now I go ahead and solve for n by dividing both numbers, and I get n equals 1. So I've gotten my rate of law equation. So the rate is equal to the constant times H2 to the power of 1 times the concentration of I2 to the power of 1. So that is going to be one of my boxed-in answers. The next thing they want us to do is solve for the rate law constant, but they want us to have the correct units also. So I like to solve for my units first. So I'm going to go ahead and rearrange this equation so that I am actually solving for K. K equals the rate over the concentration of H2 raised to the power of 1 times the concentration of I2 to the power of 1. Now I'm only working with units. So I'm going to go ahead and put in my units. The rate is molarity over seconds. And the concentration is molarity times molarity. So I'm going to start canceling out units. This molarity cancels out with one of the molarities in the denominator. So the units are going to be 1 over molarity times 1 over seconds. So I've got my units. Now I just got to solve for K. Again, we take a look at our rate law equation. And I'm going to use trial 1 because it's the first number. So trial 1 has a rate of 0.952 times K times the concentration of hydrogen, it was 1.77, times the concentration of H2. Again, you can use any trial you want to use. I've used trial 1 just because it's on top there. I'm going to go ahead and solve for K. K equals to two significant figures, 0.73, and my units are 1 over molarity times 1 over seconds. It does take quite a bit of work, but if you do it in a nice, neat fashion, you can go ahead and put all the work together and come up with your answer fairly quickly. Let's take a look at another example. They want us to determine the rate law equation and the rate law constant to two significant figures with the correct units. I want to remind myself that the rate law equation is rate equals the constant times the concentration of N2 raised to the power of M times the concentration of H2 raised to the power of N. So we're asked to solve basically for M and N, and we want to solve for K. For us to solve for M, we have to make sure that the concentration of H2 cancels out. So for us to solve for M, I want to make sure that the concentration of H2 cancels out, so that I'm looking at trial 1 and trial 3. Trial 3 has a larger rate of reaction, so I'm going to go ahead and I'm going to divide trial 3 by trial 1. For us to solve for N, I want to make sure the concentration of N2 cancels out. So I'm going to work with trial 1 and trial 2. Trial 2 has a larger rate, so I'm going to go ahead and divide trial 2 by trial 1. All right, let's get working. I want to solve for M. So I'm going to divide the rates of trial 3 over trial 1. The rate for trial 3 is 4.14 times 10 to the 5th equals K. The concentration of N2 is 1 raised to the power of M. The concentration of H2 is 2.38 raised to the power of N. Trial 1 rate is 2 times 10 to the 5th equals K. The concentration of N2 is 0.695. And the concentration of H2 is 2.38 raised to the power of N. I see that my H2 cancels out along with my K. So I'm going to divide these numbers up. 4.14 times 10 to the 5th divided by 2 times 10 to the 5th is equal to 2.07. 1 divided by 0.695 is 1.439 to the power of M. I want to solve for M, which is a power, so I have to take the natural log of both sides. This brings M down. The natural log of 2.07 is 0.7275. The natural log of 1.439 is 0.3639. 0.7275 divided by 0.3639, M equals 2. I want to go ahead and solve now for N. So I want to make sure that the units of N2 cancel out. So that means I'm going to be dividing trial 2 by trial 1. Rate equals K times the concentration of N2 to the power of M times the concentration of H2 to the power of N over trial 1 I can start canceling out some numbers here. My K's cancel out. And my M's cancel out. So 4.65 times 10 to the 4th divided by 2 times 10 to the 5th is 0.2325. 0.553 divided by 2.38 is 0.2324 to the power of n. I want to get the power of n out of the power and down to the floor so I can solve for it. So I have to take the natural log of both sides. Natural log of 0.2325 is a negative number. And the natural log of 0.2324 is also a negative number, which is good, because negative divided by negative is a positive number. So n equals 1. So my rate is equal to K times the concentration of N2 to the power of 2 times the concentration of H2 to the power of 1. But we don't actually have to put the 1, it's kind of invisible. Okay, so the next thing I like to do is solve for my units. I'm going to rearrange this rate law equation. So K equals rate over the concentration of N2 to the power of 2 times the concentration of H2 to the power of 1. I'm just going to insert my units. And see what cancels out. One of my molarities cancels out with one of the molarities. So the units of K is going to be 1 over molarity squared times 1 over seconds. Now that I have my units, I can go ahead and solve for my rate. I'm going to use trial 1 just because it's on top. The concentration for N2 is 0.695 squared, and the concentration for H2 is 2.38. So my K to 2 sig figs is 1.7 times 10 to the 5th, 1 over molarity squared times 1 over second. So I've got my rate, and I've got my rate law constant. Good luck and keep practicing.